Today, we will talk about the operation of the airspeed indicator, as well as the speeds used in aviation, with their corresponding definitions. First of all, we will divide the airspeed indicator topic into two videos. In this first part, we will focus on how an airspeed indicator works, what are the errors and corrections that must be applied, as well as the different definitions of the speeds used in aviation. In the next video, or second part, we will see the color-coded markings of the indicator, how would the instrument react to a pitted tube blockage, as well as a static port blockage. So with this being said, let's get started with how an airspeed indicator works. The airspeed indicator is one of the 6 basic flight instruments, and as we said in the previous video, this instrument is linked to the pitted static system, which means that its reading depends on the measurement of the air pressure. Let's see the schematic of the pitted static system. As we can see, the airspeed indicator is the only instrument that is actually connected to both the pitted tube and the static port. The pitted tube provides total pressure, while the static port provides static pressure, or in other words, atmospheric pressure. In order to understand why the airspeed indicator needs these two types of pressure, we must first review their definitions. As we said in the previous video about the pitted static system, static pressure is the same as the atmospheric pressure, and it is exerted equally in all directions, regardless if the object is moving or is still. On the other hand, the dynamic pressure is the pressure produced by the air when an object moves through it, and it is proportional to the speed and air density. So in other words, the faster we move, the higher the dynamic pressure, and vice versa. Finally, the total pressure corresponds to the sum of static and dynamic pressure. This means that, when measuring the pressure of a jet of air, we will obtain the total pressure as a result. Now, the airspeed indicator, abbreviated as ASI, is an instrument that indicates the speed of the aircraft relative to the air. And as we know, the airspeed is directly proportional to the dynamic pressure, so if for example an aircraft flies at 80 knots, it will experience less dynamic pressure than if it were flying at 120 knots. With this in mind, what the instrument does is that it takes advantage of this principle to measure the dynamic pressure and then give an airspeed reading based on it. We can say in other words that the airspeed indicator is actually a dynamic pressure gauge that is calibrated to indicate airspeed. This way, if the aircraft experiences a high dynamic pressure, this will be interpreted as a high speed, and vice versa. Having seen this, it is clear that the airspeed indicator needs the information of dynamic pressure in order to indicate airspeed. The problem is that the pitted tube provides total pressure, not only dynamic pressure. Now, as we said previously, the total pressure equals to dynamic pressure plus static pressure. So if we want only the dynamic pressure, we have to take the total pressure and subtract the static pressure, which is provided by the static port. This is why the instrument needs information from both the pitted tube and the static port. So basically, what the instrument does is that it subtracts the static pressure to the total pressure, thus obtaining the dynamic pressure as a result, with which it can now give an airspeed reading. If we look inside the instrument, we will see the following. Here we have the static port and pitted tube connections. However, the difference is that the static port is directly connected to the inside of the case, while the pitted tube is connected to a diaphragm, which in turn is connected to gears, which allow the needle to move in the dial. So, this would work the following way. The static port allows the whole case to be filled with static pressure, while the pitted tube causes the diaphragm to fill with total pressure. This means that the total pressure inside the diaphragm tries to expand it, while the static pressure in the case tries to contract that diaphragm. Now, as we will remember, the total pressure is static pressure plus dynamic pressure, so we can express it as a combination of these two pressures. This results in that part of the pressure inside the diaphragm is dynamic and part is static. And as the static pressure inside the diaphragm is the same as outside of it, they can be cancelled out. Now there's only dynamic pressure, which means that the expansion or contraction of the diaphragm will depend only on dynamic pressure. So for example, if dynamic pressure increases, the diaphragm will expand, making the gears move the needle to indicate a higher speed. On the other hand, if dynamic pressure reduces, this will cause the diaphragm to contract, making the gears move the needle once again, but now to indicate a lower speed. Now, there's something that we must keep in mind. And it is that the instrument is not totally perfect, which means that the airspeed indication has some errors. That's the reason why we have different speed terms and definitions in aviation. Each of these speeds is corrected by certain errors, so let's see each of them in more detail. Let's start with the simplest of all, the indicated airspeed, abbreviated as IAS. This is basically, as its name suggests, the speed indicated on the instrument, and it is not corrected for any type of error. This speed can be expressed either in knots or in miles per hour, depending on the instrument design. For example, here we have one which is indicating 70 knots, and here we have another that is indicating 70 miles per hour. In many cases, the instrument includes both speed scales, as we can see in this example. Here the outer scale corresponds to miles per hour, while the inner scale corresponds to knots. Having already seen what is the indicated airspeed, let's see some errors that are produced. The first is the instrument error. This is produced due to manufacturing imperfections and wear of the gears inside the instrument. The second type of error is the position error that we already discussed more in detail in the video about the pitot static system. This is produced due to changes of flaps and gear configuration, changes of angle of attack, and some other maneuvers. This error affects directly the pressure measured by both the pitot tube and the static port. The combination of these two errors leads us to the next speed term, the calibrated airspeed. The calibrated airspeed, abbreviated as CAS, corresponds to the indicated airspeed corrected for the instrument and position errors. In other words, if we take the airspeed indicated on the instrument and we correct it for these errors, we will obtain the calibrated airspeed. Now, the question is, how is the calibrated airspeed determined? Well, in order to do so, the manufacturers designed special tables of airspeed calibration, which are based on certain configurations and speeds, and they are published in the aircraft manual. In this example, this is an airspeed calibration table for a Cessna 172. Now, let's suppose for example that we want to know what would be the calibrated airspeed if we fly with an indicated airspeed of 100 knots, with the flaps extended to 10 degrees. In this case we have to refer to the row of flaps 10 degrees, and we can see that we have both the indicated and calibrated airspeeds. Here, as a side note, when speeds are expressed in knots, it is common to include a K before the speed term. Now, in the table we just have to look for 100 knots of indicated airspeed and then read the corresponding calibrated airspeed of 98 knots. As we can see, the difference between the indicated and calibrated airspeeds is quite small, therefore in practice, it is common to assume that the indicated and calibrated airspeed are roughly equal. Let's now move on to the next type of error, which is known as compressibility error. In the design of the pitot static system, the air is assumed to behave as an ideal gas, and one of the characteristics of an ideal gas is that it cannot be compressed. However, the reality is that, when flying at high speeds, the air actually compresses, thus generating certain errors in the measurement of airspeed. Normally the compressibility effects start to become significant above 300 knots, therefore this error is almost nil in small and slow aircraft. But if we fly at high speeds, we must then add a compensation for the air compressibility factor, resulting in the following speed term, the equivalent airspeed. The equivalent airspeed, abbreviated as EAS, is the calibrated airspeed corrected for compressibility errors. So in other words, if we take the calibrated airspeed and we apply the compressibility errors correction, we get the equivalent airspeed. Remember that this compressibility error correction is only carried out when flying at high speeds, and the truth is that calculating this correction manually can be a bit complex. That's why normally this correction is automatically calculated in real time by the avionics computers of the aircraft, so the pilot doesn't have to worry about this correction. Having seen this, let's continue with the other type of error, the density error. As previously mentioned, the dynamic pressure depends not only on the speed of the aircraft, but also on the density of the air. In other words, the indication of the airspeed indicator will not only depend on the speed of the aircraft relative to the air, but also on the density. Let's see this by means of an example. Here we have two pitot tubes from different aircraft. In this case, the tube at the top will move in air with lower density, which means that the air particles will be farther apart. While the tube at the bottom will move in air with higher density, which means that the air particles will be closer together. In this case, we can observe that the tube at the top, as it moves in less dense air, it captures less air particles, which means that it experiences a lower dynamic pressure, and therefore the airspeed indicator will show a lower indicated airspeed. On the other hand, the tube at the bottom moving in denser air captures a larger amount of air particles, which means that it experiences a higher dynamic pressure, and therefore the airspeed indicator will show a higher indicated airspeed. So, we can see that, although both tubes are moving at the same speed through the air, the simple fact of moving in different densities result in different indicated airspeeds. That's why the airspeed reading needs to be corrected by density error, which gives as a result, the true airspeed. The true airspeed, abbreviated as TAS, is the airspeed corrected by density error, and as we know, the density of air depends mainly on temperature and static pressure. We can also say that this is the actual speed of the aircraft in relation to the air, since we've already applied all necessary corrections. So, in order to know how to apply this density correction, it is necessary to first understand how density behaves in the atmosphere. In this case, the higher the altitude, the lower the static pressure, which also means less air density. This means that if we take two samples of air, one at sea level and the other at 10,000 feet, we will have less density at 10,000 feet. And since there is less density, an aircraft flying at that altitude will experience a lower dynamic pressure, therefore the airspeed indication will not correspond to the true airspeed. Something important to note here is that the instrument is calibrated to indicate the true airspeed only at sea level under standard conditions. So in other words, the airspeed indicator assumes that the density is always that of sea level and with standard temperature. This means that at sea level, the indicated airspeed and the true airspeed will be roughly equal. However, as we climb and the density starts reducing, then this relationship will change. Let's see an example. Here we have a column of air from 0 to 10,000 feet, and we can see how density changes with altitude. In this case, we are going to assume that the conditions are standard, that is a sea level pressure of 2992 inches of mercury and a temperature of 15 degrees Celsius. With this in mind, let's suppose that an aircraft flies at a very low altitude, close to sea level, and its airspeed indicator shows 100 knots. Since near the sea level the indicated and true airspeeds are roughly equal, the true airspeed will also be 100 knots. However, if the aircraft flies higher, in lower density air, and its indicator also shows 100 knots, that would mean that the aircraft must be flying at a higher true airspeed. In this case, 120 knots. In this way, the true airspeed continues to increase as we climb with a constant indicated airspeed. The question is, how do we calculate this true airspeed? Well, there are two main methods. The most precise is by means of a flight computer, either manual or electronic, but we are not going to get in detail with it. The other method is by means of an approximate formula, and it is based on the rule of thumb which says that the true airspeed increases by 2% for each 1,000 feet of altitude increase. So knowing this, we can apply a simple rule of 3 to determine the percentual increase of the true airspeed at a certain altitude. Let's see these two methods by means of an example. Suppose we need to determine the true airspeed based on an indicated airspeed of 110 knots and under the following conditions. A pressure altitude of 10,000 feet and an outside air temperature of 5 degrees Celsius. Let's first use the formula. So if we know that, for every 1,000 feet of altitude increase, the true airspeed increases by 2%, how much will it increase in 10,000 feet? If we do the math, the result is a 20% increase. With this information we could do two things. We can multiply 110 by 0.20, giving as a result the 20% of 110, which is 22 knots, and then add those 22 knots to the initial indicated airspeed of 110 knots, obtaining a true airspeed of 132 knots. The other way, which is a lot simpler, is to multiply directly 110 by 1.20, which is the same as obtaining the 120% of 110, giving as a result 132 knots of true airspeed. Either of these procedures can be performed, and the result will be the same. Let's see now what the result would be in case of using a manual flight computer. First, we have to align the air temperature of 5 degrees Celsius with the pressure altitude of 10,000 feet on this inner scale. Then we look for 110 in the middle scale, and finally we observe that it corresponds to approximately 130 in the outer scale. This means that the resulting true airspeed is 130 knots. Now, apart from these two methods, there is one more that can be used while flying, and it is by means of the true airspeed scale of the airspeed indicator. As we can see, some instruments include a sliding true airspeed scale incorporated, so let's see how it's used. We must first use this knob in the bottom right corner to adjust the current pressure altitude with the outside air temperature on this scale of the top, just as we did with the flight computer. Once this is done, the scale below will be adjusted to indicate the true airspeed for any given indicated airspeed within the scale. For example, this particular instrument shows an indicated airspeed of 175 miles per hour, and then on the true airspeed scale we can read approximately 202 miles per hour. So, in this way, the pilot can determine the true airspeed in real time easily. Now, we will look at the last speed term, the ground speed. The ground speed, abbreviated as GS, is the actual speed of the aircraft in relation to the ground. And it corresponds to the true airspeed corrected by wind. First of all, let's see how the wind affects the speed of an aircraft. When an aircraft experiences a tailwind, it will literally be pushed by the wind. In other words, its speed in relation to the ground will increase. On the other hand, if the aircraft experiences a headwind, it will be slowed down by the wind. In other words, its speed in relation to the ground will decrease. That's why, in order to determine the ground speed, we must apply the wind correction. First, we must see what happens when there's no wind. In this case, the true airspeed and the ground speed will be equal. Let's see an example. Here, this aircraft is flying in calm air, which means that there's no wind. If this aircraft flies at 100 knots of true airspeed, this means that it is flying at 100 knots in relation to the air mass. And since the air mass is not moving, the speed in relation to the ground will also be 100 knots. Now, if we experience a headwind, the ground speed will be less than the true airspeed. Let's see why. Here the aircraft is flying with a headwind of 20 knots. This means that the air mass is moving against the aircraft at 20 knots. Here, if the aircraft is moving at 100 knots in relation to the air mass, we will observe that its speed in relation to the ground will be 20 knots lower, so the ground speed will be 80 knots. The opposite happens when there is a tailwind. In this case, the speed in relation to the ground will be higher than the speed in relation to the air. For example, here we have an aircraft that is flying with a tailwind of 20 knots. Here, the aircraft travels through the air mass at 100 knots, while at the same time, the air mass is moving in the same direction at 20 knots. This means that the aircraft is moving at 120 knots in relation to the ground. With this, we have already seen all the speed terms and definitions. Let's see a little summary. If we take the indicated airspeed and we correct it for instrument and position errors, we will get the calibrated airspeed. If then we apply compressibility corrections, we will get the equivalent airspeed. If then we apply density correction, we will get the true airspeed. And finally, if we apply wind correction, we obtain the ground speed. Now, some aircraft perform these calculations automatically in real time by means of an air data computer. However, if the aircraft is not equipped with this avionics computer, the pilot will have to do these calculations manually. In that case, something important to note is that in practice, it is normally assumed that the indicated airspeed is roughly equal to the calibrated airspeed. And apart from that, if we fly at low speeds, below 300 knots, we will have little influence of compressibility effects, so we can say that the calibrated airspeed is roughly the same as the equivalent airspeed. So with these assumptions, we can say that if we take the indicated airspeed and we correct it for density error, we will obtain the true airspeed, and then if we correct it for wind, we will obtain the ground speed. This simplified procedure is the one that is normally performed in day-to-day operations. Now, another important thing to mention is that it is important to understand the definition of each of these speeds, since each one is used for different purposes. Let's look at some practical applications of these speeds. We know that the indicated airspeed depends directly on the dynamic pressure. Therefore, it is useful to establish structural speed limitations, takeoff and landing speeds, stall speeds, and some performance-related speeds, such as the best glide speed, Vx and Vy. On the other hand, the true airspeed is the actual speed of the aircraft in relation to the air, and therefore, it is used in the ATC flight plan, the calculation of the Mach speed, endurance calculations, wind correction angle determination, and general flight planning aspects. Finally, the ground speed is the actual speed of the aircraft in relation to the ground, and therefore it is used for calculating flight time, fuel consumption, climb and descent parameters, and some other general flight planning data. I hope the information presented in this video has been useful. If so, don't forget to share, like, subscribe, and leave a comment down below. Thanks for watching.